Good afternoon. I'm Carl Blumstein. I'm the managing director of the Citrus I4 Energy Center. I'm going to introduce the speaker, but first a few announcements. I want to welcome web viewers from our other campuses. We're starting a new seminar series in conjunction with the Institute for Transportation Studies and Trust. That's another acronym, but I don't know what those letters all mean. But it's about cybersecurity, focused on resilience. The new seminar series will be focused on resilience. It'll begin in March, and details are online. The next deadline for the Foundry at Citrus is February 22nd for the spring 2015 cohort. They're looking for highly motivated teams who are ready to make a significant impact on the world. We like ideas that are original, scalable, and financially viable. Our facilities are set up to best assist teams that have a hardware component to their project, but we also support software-focused solutions. So check out the Foundry on the Citrus website. Tomorrow at noon is the sold-out Berkeley Innovators Series. Mark Tarpening, co-founder of Tesla Motors in Sudharjadai Hall, here in this auditorium. Whether there'll be some people who don't show up, there usually are. If you're interested in hearing from Tarpening, I think he's no longer active at Tesla, but if you got here early, you have a reasonable chance of getting one of those vacancies. Now to introduce the speaker, who's I'll read what it says, and then I have a few words on my own. Meredith Fowlie is an associate professor in the Department of Agricultural and Resource Economics at Berkeley. She's an applied economist working at the intersection of industrial organization, energy markets, and environmental economics. Much of her work investigates how market-based environmental regulations and emissions trading programs, in particular, are working in practice. She is also interested in the demand side of energy markets and work that integrates methods and models from other disciplines into economic analysis of policy outcomes. She's also a former graduate student at Berkeley, where she got a degree in economics and worked at the UC Energy Institute for 6-7 years, or I don't know, however long it was. But she's a fabulous person, terrific economist, and a great presenter. So we're really lucky to have her here at Berkeley, and I think we have a great seminar lined up for you.
Great. Thank you, Carl. Carl, I've known Carl for a while. He's been a great mentor. He's sort of a senior statesman in this space. So I always look for Carl's comments on projects that we're working on or trying to launch, and he's offered some comments on the work we're going to be doing here today. So thanks very much, Carl, and to Citrus for the invitation. So like Carl said, I'm a trained as an economist. All of my work has something to do with energy. Most of it is pretty policy-driven. When I first started, I was really focused almost exclusively on the supply side of energy markets, and in particular, power production, renewable energy, conventional generation, thinking about how to design policies to encourage cost-effective reductions in emissions and environmental impacts of energy production. But increasingly, I have started to look over to the other side, on the demand side, for a number of reasons. One is the data are quite rich, and increasingly researchers are gaining access to these data. So that really cracks open the possibilities of launching research agendas that just weren't possible in a more sort of data poor environment. And the other reason is just sort of my appreciation. It's sort of obvious to many of you, and has probably been obvious to several in this room for many years, that the demand side has a real role to play in advancing progress towards cleaner and more reliable electric systems. And in that capacity, there's sort of two big ideas, and again, ideas that are familiar to probably everyone in this room. One is just improving the efficiency of demand-side energy consumption, so reducing the energy required to deliver energy services. And the second is demand response. And basically what that involves is incentivizing or paying energy users to reduce consumption and respond to some changing market environment. Right now, we think mostly about programs that are designed to reduce peak demand. But looking forward, and people are already starting to think more creatively about this, demand response has real potential in terms of reducing the cost of renewables integration and just easing the transition to power systems with higher penetration of renewable energy and the intermittent sources in particular. So these are the two big ideas that we'll be focusing on in this short presentation. And I think we can all agree, or most of us can agree, that in general these are good ideas. We want more energy efficiency. We want more demand response. I could have picked any number of nice pictures generated by governments, research groups, think tanks that show this projected increased role for energy efficiency in meeting emissions reduction targets and environmental goals. So, the size of that wedge varies across graphs and across perspectives, but in general, we're expecting more energy efficiency and really pinning our hopes on energy efficiency in terms of mitigating the environmental impacts of energy production and consumption. We can all agree on, yes, we want more, but then that leads to a more nuanced question of, but what kind of energy efficiency, how much investment in energy efficiency? This is a picture that many of you may have seen. There are other pictures like it. This particular picture was generated by McKinsey. And the basic idea here is to look out into the economy and think about all the possible efficiency improvements that could be made. More efficient appliances, improved lighting, more efficient buildings, and thinking about the cost of those investments and also the energy efficiency or the energy savings that could be gleaned from making those investments. I would say a lot of the evidence that informs energy efficiency investments both today and that $130 billion I just grabbed from the IEA is their estimate of current global spending on energy efficiency. So those numbers vary, but they're all big. Thinking about the evidence that's informing these efficiency investments, that evidence is coming from what economists typically call, although my husband, the engineer, it sort of grates on him, as these engineering models. So basically analysis that thinks about technology performance, energy savings potential in sort of a forward-looking way and estimates the costs of these various investments and the energy savings that could result, right? There's mounting evidence that in some contexts, this type of analysis can overstate the savings that actually manifest in real-world settings. And it's not always true, but certainly we're increasingly seeing documented evidence that sometimes those engineering projections could overestimate the savings that actually are realized. And so I think one of the jumping off points for this sort of research that I'm going to be talking about today is the need for also ex post empirical analysis of realized energy savings associated with these different possible interventions in order to inform policy decisions and investments going forward. Switching gears a little to think about demand response. As many of you know, we've made significant investments in expanding the smart grid and associated technologies. This is just a graph or a map showing you penetration of smart meters as of 2014, and that penetration continues to increase. So whereas it's estimated that 33% of households are currently equipped with smart meters, and that number is rising, a very small percent are actually on time-based or dynamic pricing type rates. And so that just suggests that there's more we can do to leverage our investment in smart grid infrastructure and associated technologies and sort of increase the responsiveness of the demand side. But here again, same sort of idea, right? We can all agree we need more, and there's much more we can do to elicit efficient demand response, but how to effectively mobilize it, there are different pricing structures, there's different customer subpopulations. So again, more research to understand what's working well and where to target our efforts, I think, is really critical as we look ahead to trying to scale up the demand response from electricity customers. So the jumping off point for this talk, and I should have said, I was going to say this at the beginning, I understand that the culture of this talk is to not really interrupt with questions. I'm not used to that. It makes me a little uncomfortable. If you have clarifying questions, please don't hesitate to interrupt me. Maybe the longer back and forth discussion could be saved for the end, but if there's something that's not clear, don't hesitate. It'll make me feel at home to be interrupted. So there's broad-based support for increasing demand-side energy efficiency and mobilizing more demand response. But these questions of exactly how to do that, I think, are really important questions. And so that's sort of the research I'm going to be summarizing today. So the basic layout for the talk is, first of all, just to talk a little bit about the methodology we're using. It's not a silver bullet, but I think it's an important set of tools that we can bring to these questions. Talk about 3 applications, just sort of touch on them. We don't have much time, but I want to give you a feel for what we're doing and how we're using these tools in these different settings, and then just conclude. So the fundamental challenge when you just think about the general questions I'm posing here is you've got an intervention that you care about and you're interested in. Maybe it's an efficiency improvement, more efficient appliances. Maybe it's a dynamic pricing program. and you're interested in estimating the causal impact of that intervention on some energy outcome you care about. So it could be peak demand, could just be patterns of consumption in a specific customer population, right? So it's basically a causal question. As I mentioned, we've got a bunch of evidence coming from these more ex-ante simulation type models and methods. We've also got a wealth of studies that are more data-driven. So the basic flavor of these studies is look at the group of households or firms that have either adopted the technology we're interested in evaluating or have selected into a program that we're interested in evaluating, and compare them to households, firms that have not adopted that technology or have not taken up that program, and compare the outcomes across those two groups. And of course, the concern that is always sort of there is that even if you really control to the best of your ability for observable covariates, right, so gender and age and income, they all look the same across the adopters and the non-adopters, or the program taker-uppers and the non-program taker-uppers, there's still something different about those two groups, right? There's something that meant that household bought the more efficient washer, or that household selected into the critical peak pricing program. And you're always concerned that those unobservable differences are going to confound your ability to really credibly estimate the causal impact of that intervention, right? The factors that led me or my husband, who is the real efficiency enthusiast in our house, to adopt the really efficient washer, those unobservables also affect how he uses energy sparingly and could really affect the energy outcomes we're really interested in caring about. So what we're picking up is some combination of the intervention and those unobservable factors, right? So that's the challenge of causal inference when we're thinking about identifying these impacts. So the textbook approach to this problem is, you've got your vials and your placing. This woman, I think, is working with avocado plants here, and we'll talk about the fact that electricity consumers are not like avocado plants. But in order to deal with this identification problem, what you would ideally do is you randomly assign your intervention, right? You take a random sample from a population and you divide that sample into two groups, and you randomly assign one group the treatment or the intervention, and you leave the control alone, and you compare outcomes across those two groups. And the beauty of that design is that all those unobservables you're worried about are identically distributed in expectation across those two groups, such that a comparison of outcomes yields the causal impact. So in a typical presentation, I would use math. In 40 minutes, I'm going to use cartoons to fix ideas, right? And this is where, please ask me questions, because cartoons don't tend to be as precise as math, but they're faster and hopefully more fun as you eat your lunch. So we've got this big red egg that's your population of interest. It's electricity customers in Michigan. It's newly electrified households in India. And you randomly sample from that population to get a manageable sample for your study. And the random selection there is just guaranteeing that the composition of your sample, observable and unobservables, is identical in expectation to the larger population you want to learn something about. You divide your little yellow egg into two pieces. It doesn't have to be equal pieces, but I'm going to use equal pieces because it looks nicer. Half is just your control group. You don't touch them. And half is assigned to your treatment, your dynamic pricing program, your efficiency improvement, et cetera. And so with perfect compliance, meaning all those assigned guys to treated are actually getting their treatment, and all those control guys are untouched by your intervention, when you compare those two outcomes and take the difference, because observables and unobservables affecting your outcome are identically distributed across those two groups, the difference in, for example, peak energy consumption across those two groups can be interpreted as the causal impact of your intervention on energy consumption in this population, right? Beautiful. But there's a problem. Unlike our avocado plants that we're putting in the vials, when you put a household into a dynamic pricing program, they call their utility and say, I don't want to be here, get me out. Or, so you can imagine that when you randomly assign households to control or treatment groups, people move around, right? And rather than throw up our hands in defeat, basically what we do is we design experiments and analyze experiments in a way that accommodates that imperfect compliance, right? So imperfect compliance is just a fancy term that means, you put someone in a treatment group and they don't take up the treatment. Or we're not going to look at this in this picture, but you assign someone to a control group and they find a way into your intervention in their own way. So back to our eggs. You can imagine what's going to happen if, here's your assigned to treated group and only this little blue egg actually gets treated, right? And so were you to compare the treated guys to everyone in your sample who didn't get treated, you're back to worrying about unobservables, right? Because it was a non-random process that got these guys into the treatment, right? There's something different about these guys and these guys. And similarly, if you compared outcomes, let's say energy consumption among your treated to your control group, you're still concerned because the composition of the folks in this treated subset is not by design equal to your yellow control group, right? Because there's this non-random selection happening, and you're worrying about those unobservables confounding your ability to measure the causal impact of your efficiency improvement or your demand response program. So what do? We do what's called a randomized encouragement design. We didn't invent it, but it's increasingly used by economists and other social scientists and other natural scientists whenever you run into an imperfect compliance problem. And so just to give you a flavor for this, without getting too mired in the details, the basic idea is the following. You sort of imagine your sample here is comprised of two types of people in this setting. We're going to call them never takers and compliers. The never takers never take, right? So they are not interested in your demand response program. They're not going to take it up if they're in the control group, but if you assign them to treatment or if you encourage them into the program, they're not going to take it, right? So they are these guys. They're in the green. They're out here. You encourage them or you assign them to the program, but they're not taking it up, right? And they are present in equal proportion in the control group, right? Because random assignment assigns equal proportions across your two sides of this egg. Does that make sense? Then you've got the compliers. If they're in the control group, they're not encouraged or assigned to treatment, so they're still in the control state. They're not taking up your demand response program. They're not adopting the efficient appliance. But if you put them in, if you assign them to treatment or if you encourage them into treatment, they take it up, right? So what does that buy you? Now we're going to compare the average outcomes between the two halves of our sample egg. Peak consumption, average peak consumption in this egg, average peak consumption in this half of the egg, right? The contribution of the never takers to those, you can think about each half, the control group, the outcome is a weighted average of the peak consumption among the never takers and a peak consumption among the compliers, right? So when you compare average outcomes across these sort of control and assigned to a treatment or control or encouraged groups, you're comparing two weighted averages. The contribution of the never takers cancels out, right? Never takers are always in the control state. And now what you're left with, I need my egg back, what you're left with is the comparison of the compliers in the control state in this subgroup and the treated state in this subgroup. So what you're able to do with a randomized encouragement design is identify the effect of the intervention on the compliers, on that subpopulation who, if assigned to treatment or encouraged to treatment, would take up the program. Mechanically, what you're doing, and this might be a little bit too much for a lunch talk, is comparing average outcomes across these two groups and dividing by the proportion of the population that are compliers. And you can identify that proportion by just looking at the fraction of your encouraged or assigned to treatment group who take up the treatment. Does that make sense? So what I'm going to show you is 3 applications of this research design, which basically involves sampling randomly from our red egg, dividing our sample into an assigned to treatment or encouraged group and a control group, observing not only outcomes, but who takes up the treatment in the encouraged group, and we'll even look at a research design that allows some of the control group to take up the treatment, and estimating this average effect on the compliers. Right? Because
Meredith,
we have,
I have a question
yes,
for you.
Yes.
And by the way, people who have questions can raise their hands, and I'll give them the mic, because we do have some people on the web, or you can repeat the question.
Okay.
But I have a mic, so.
Great.
So my question is to do, so the treated compliers presumably include some people who didn't need to be encouraged in order to comply.
Yep.
And the untreated compliers are people who also, let's suppose compliance is get attic insulation. Mm-hmm. So you have, in the untreated compliers, you have people who got attic insulation and weren't encouraged.
No, we observed them getting attic insulation. That's key.
They got it, but they weren't encouraged to get it.
Right, but what the key here is we observe not only your outcome, which is energy consumption, but your treatment status, which is attic insulation. So let me go to one here. So I think what you're doing is saying there's going to be research designs where some of the guys in your control group take up your attic insulation.
Yes.
We observe that. For a
yes,
randomized
right.
encouragement design, you got to observe that.
But are those the untreated compliers?
So one more piece of jargon. Okay. They are the always takers. So if you have a research design where you have some treated guys in this side of the egg, we need another subset of the population, which is always takers, who's guys who get treated regardless of whether you assign them to the control or assign to treatment group.
Okay.
And the research design works identically in the sense that you're comparing average outcomes across these two groups. The always takers the contribution of the always takers cancel out. If people can understand what I'm doing, I'm pointing at this egg. But the always takers are treated in both states, right? So their contribution to this average outcome is going to cancel each other out because the always takers get attic insulation regardless of whether they're assigned to the control or assigned to the treatment. And so a randomized encouragement design is able to identify the effect of attic insulation on energy consumption among those people who would only get attic insulation if assigned to the encouraged group. It cannot tell us the effect of attic insulation on people who, no matter where we put them, they're going to go to Home Depot and get their attic insulated. Does that make sense? Yeah?
I'm working on it.
Okay. Other questions? Because this is like, I don't want to spend too much time on it, but I do want to make sure I spend enough time so people get the flavor, because this is the machinery we're going to pick up and move from Michigan to California to India if we get time. Yeah?
Okay. In the encouraged group, these ones that are the this actually treated group, these always compliers.
So just to be one clarifying, the actually treated in the encouraged group include compliers and always takers.
Yes. So the always takers. In kind of parlance of in the EE industry, would that be the grouping of free riders? Or is that really not a helpful thing?
I would not introduce that because I think it's going to confound.
Okay.
Yeah, if you don't mind, if we set that aside.
That's fine.
Yeah, I mean, I think it's partly yes, but I don't want to. Yes.
Okay.
Is there one more question for me?
Yeah, I'm wondering how you take into effect the effect of social dynamics. So like social media, I mean, are these people friends?
Yep. This is a great question, and one that I was going to bring up at the end with caveats, but let's bring it up now. So what's this? What this is? We're okay. Well, we're okay if sort of our encouragement. There's spillovers, right? So what the framework underlying this is assuming that my outcome is a function of my own treatment, right? My own treatment status, right? So you can imagine that if there's some peer effects that could complicate the interpretation of what we're able to estimate. I think let me say one thing and then we'll maybe see if this is clear enough to move on. I think we're okay if the encouragement, this is a complicated thing. I think the short answer is that spillovers do complicate things because if there's peer effects, then we're part of the control group is getting treated as a consequence of our encouragement and may not be a perfect estimate of what we would observe in a different setting. But in some senses, if what we're in, I think I'll leave it. It was a poorly answered question. Spillovers are a complication. Let's just leave it at that. And if the treatment is purely a function of your own treatment status, then we're okay. Things get more complicated if how I respond is a function of not only my treatment, my attic insulation, but also the treatment status of others around me. Is that good? And then realize I didn't nail it, but at least hopefully, yes, it's a concern, more of a concern in some places than others. Okay, so let me keep going if we're okay with that. That's the basic. Hopefully this will become more clear as I show you how we apply this in different settings. And then we'll come back to good questions like concerns about spillovers. First application, weatherization in Michigan. Joint work with Michael Greenstone at Chicago and Catherine Wolfram at the Haas School of Business. General support supported by several foundations and organizations, including Becky here at Berkeley and UCE3. So very grateful to all these sources of funding for this, what I think is an important project. Key objective that I want to focus on here is this is a large-scale field experiment in Michigan that was designed to measure realized returns on investments in residential weatherization, energy efficiency upgrades in low-income households. What you need to know to just make sense of this is the largest residential energy efficiency program in the country. 7 million participants to date, but it's been running for many, many, many years. Retrofits, weatherization, sort of that word conjures up in your mind is about what people are getting. So new furnaces, new insulation, new water heaters, window caulking, etc. Average expenditure in our sample is about $5,000 per household. So not a small investment. No monetary cost to the household. So how this works is you're a low-income household, you sign up for the program, a non-trivial exercise, an audit team comes to your home, does some cost-benefit analysis, recommends measures, and then taxpayer-funded retrofit happens, right? You have to stay home for the audit, et cetera, but the measures are funded by the program. We work in Michigan for a number of reasons. Michigan's cold, lots of weather, lots of low income, so large eligible population. And they received a lot of funding during the time period which we were studying or working, which is the ARA period. Under the stimulus package, a large increase in funding for the program, which allowed the program to scale up. So I would argue a randomized encouragement design is well suited to this setting for a number of reasons. First of all, non-random selection into the program is a concern, right? So the type of households who take up weatherization on their own steam could be very different in observable and unobservable ways from households that look similar but don't choose to take up the program. Clearly, we couldn't have a mandatory assignment to treatment. We couldn't break into people's houses with a caulk gun and start weatherizing and forbid perfectly eligible households from signing up for the sake of research design integrity, right? That's just not, it's off the table, and there's all sorts of reasons why that's a bad idea. And there was some interest among implementing agencies about the impact of encouragement on program take-up. So there's all sorts of reasons why a randomized encouragement design could be useful here. Back to my egg. Randomly sample from a population of eligible Michigan households, low income, gas, heat, because we were measuring gas and electricity, assigned to a control and an encouraged group, and I'll talk about what the encouragement was in a minute, and observe not only energy consumption before and after our treatment assignment, but also who got treated. And here we have some always takers, right? We have folks that we assigned to our unencouraged group who got weatherized. What was the encouragement? I'm not going to spend too long, but this was like over a year of blood, sweat, and tears. It was 7,500 households approximately assigned to our encouragement group. We worked closely with a grassroots organization to visit these people at their homes, explain the program, help them fill out paperwork, drive them to the implementing agency if needed to submit applications, et cetera. So a lot of effort, and about $50 per household assigned to our encouraged group just to try and encourage these guys to take up the program. Quick, I'm working through it quickly. I'm hitting the high points, but ask questions if you have them. So a lot of numbers here. Let me tell you what these numbers are telling us. The base rate, this is the take-up rates in our control group, the guys that we didn't touch. We watched them, but we didn't touch them. 2% submitted application, 1% actually got weatherized in that control group, which is a really low, to us, surprisingly low rate, given that this was a sizable investment in energy efficiency improvements. But keep in mind, these are low-income households with lots of other issues looming large as they live their daily lives and maybe don't want to drop everything to take up this program. After all that encouragement, we were able to increase the take-up rate to 15%. So this 0.13 represents the incremental increase as a consequence of our encouragement. And at the end, we had a 6% weatherization rate versus a 1% weatherization rate. So the first finding, which was surprising to us but not surprising to some, is just it's really hard to get people to take up this energy efficiency improvement, which in some senses is free, but in other senses is costly because it takes a lot of effort, even with our help, to enroll for the program. Second key finding, and this is the randomized encouragement design, sort of like this is what we're gunning for, which is the estimated impact of this weatherization intervention on energy consumption, this is in percentage terms, among those households who we were able to encourage into the program. Right? So that's the difference in the two sides of the egg divided by this proportion of compliers. So what we're finding here, these are the logs. So just quickly, this is roughly over a 20% reduction in gas consumption. The vast majority of these measures targeted gas consumption, like over 90%. So we really tend to focus on gas. We also find that's a noisier estimate, but still a 10% reduction in electricity. But this is an economically significant and statistically significant reduction in gas consumption. A huge assist to households with high energy burden. So second point, I guess, relative to our first result, this is a significant reduction in energy consumption as a consequence of these interventions. However, our estimates amount to less than a third of the engineering projected savings. So quite a bit less than what was projected. Now, there's a number of reasons for this, and we talk about several in the paper. One I want to flag, because it's one that would probably is occurring to many people in this audience as they think about who we're dealing with. I'm a low-income household. You retrofit my home, you've effectively lowered the cost to heat. And if I'm income cash constrained, a very rational response to that would be to turn up the thermostat, right? And that's a gain to me. That's a rational response that you might expect. So one thing we did to try and assess the extent to which that could explain this, what we're calling measurement gap, the gap between the expected forecast savings and what we measure, is to randomly select a subset of weatherized and unweatherized households over a year after the weatherization, encourage them to let them into let us into their house on a cold, dark Michigan winter evening with two different weather thermometers and measure the indoor air temperature after closing the door for a couple minutes. This is an imperfect measure of rebound, right? But it's sort of the best we could come up with. We find a small, like 0.77 degree increase in the indoor air temperature in the weatherized homes. So if that was the extent of the rebound, that doesn't come close to rationalizing or explaining the difference between the forecast savings and our realized savings. But we do recognize that's one measure of many other. They could be heating more rooms. There are other margins they could be changing and increasing their demand on. But Our first pass suggests that rebound may be there, but it's quite small and doesn't come close to explaining the difference between projected and realized savings. So I think, in conclusion, I want to leave time for the other projects or applications. This first stage came as a surprise, yes?
I sort of related to an earlier slide also. If I recall on one of your earlier slides, one of the criteria was that the ratio had to be greater than 1 in terms of savings. And I wasn't clear if that meant in like total savings, like even for the taxpayers who funded it, so forth, or it was just the consumers who ended up with the place.
I should have been clear. So from a program implementation perspective, so the Weatherization Assistance Program, it's sort of from a taxpayer perspective in the sense that the net present value of the energy savings, based on engineering calculations of the life of the project and the energy saved, needs to exceed the cost. So that's and they use retail rates as a measure of the value of the energy saved. So it's basically like energy bill reductions to the customer over the life of the intervention need to exceed the cost to the taxpayer of that intervention. Does that make sense?
I see. And do you ever do like the carbon footprint aspect of it?
Yes. So in the paper we use a different number. We basically say, okay, we don't want to use the retail rates. We'll use the wholesale rates because that's you don't want to use the fixed cost component. But we take the wholesale rates and add using $38 per ton as a value of carbon displaced, and it's still the case that these investments don't appear cost-effective based on our estimates. So the key points here, I think that realized energy savings significant but fall short of projections. I do think that our findings underscore the importance of field testing because they should be taken in addition to these other approaches to evaluating returns to efficiency investments. And the other reason that this paper seems to be attracting some attention from policymakers is it does serve to demonstrate how you can use a randomized encouragement design to estimate the impacts of an intervention on compliers, on a subset of the program participants, in this case, the majority of participants, without really mucking up the way the program is implemented, right? We were running around the sides of this program trying to nudge in a random sample of the eligible consumers or households, but we weren't really changing the way the program was being implemented, which is important from the implementing agency's perspective. Okay, I'm going to leave it and transition, take you like out of Michigan to California, and maybe take questions, more detailed questions after. Okay, so we really need to change gears here. Low income, weatherization, Michigan, electricity pricing, critical peak pricing in particular in California. And I should say this is joint with a bunch of people, including several folks up at the Berkeley National Lab, Catherine Wolfram here at Berkeley, Steve George, and Michael Sullivan from Nexent, Jennifer Potter from SMUD, who's our utility partner. A little bit of background. Back in 2009, still in stimulus land here, a bunch of money dedicated to expanding the smart grid. And in one competitive grant process, the Department of Energy said to utilities, we're inviting proposals and we really encourage you to try and craft a proposal that incorporates experimental program evaluation methods, which was music to our ears. And Lawrence Berkeley National Lab oversaw this technical advisory process, and Catherine and I were very fortunate to be assigned to the technical advisory group helping SMUD, which ran just a really beautiful, beautiful experiment. So they ran several experiments, and in this short time frame, I'm only going to focus on one arm of a very exciting suite of experiments. And I'm going to focus on the arm that looked at critical peak pricing. For those of you, I suspect many of you in this room spend more time thinking about critical peak pricing than I do, which is saying a lot. But for those of you who aren't familiar with the concept, the basic idea is this. There are power plants in this state and elsewhere that we run like 1 or 2 hours a year, right, when peak load is really high. Because electricity is costly to store, we're balancing supply and demand in real time, and so when everyone's running their pool pumps and wine coolers and whatever else they have, and they don't see just how high the wholesale price is, we run these power plants that are designed to just meet that peak load. That's not the most efficient way one could imagine operating these markets, and if we had more response from the demand side, if we could send a signal that this is a peak hour and we'll compensate you to bring your peak down, that could be a much more efficient way to run these markets. And so that's the basic idea behind critical peak pricing, that we send a signal on those critical peak events for people to reduce their peak consumption. So what I'm showing you here is another sort of cartoon version of what a critical peak pricing structure might look like. And this is actually from the utility we're working with. You basically say, okay, relative to your current rate structure, which here it's sort of a tiered rate structure, you will pay a little less in most hours when we're not in a critical peak event, But on those peak events, you will be charged a very high price, 75 cents a kilowatt hour, giving you a very strong incentive to reduce your demand on those hours. So here we've got between 4 and 7 on up to 12 days a year. Folks on this program saw a very, very high price, but on all the other days, they paid a lower price than they otherwise would have. Does that make sense? Okay. So it makes perfect sense, but if you're like me, when you get the shiny piece of mail that says join our program, you just send it to the recycle bin. My husband takes it out of the recycle bin and calls the 1-800 number, but a lot of us just don't pay attention, right? So what we did was we had 3 groups now. Our egg gets more complicated. So we have a control group. We have one treatment where customers were given the option to opt into this program. Lucky you, here's an opportunity, call this number, send us an email, etc. And then another group was given an opt-out treatment, which basically said, same brochure, same cute kid running through a sprinkler in the summer, but it said, lucky you, you've been put in this program. To get out, it's very easy, call this number, send us an email, but the default is you're in this program. So now we've got the never takers, who regardless of what treatment they're put in, they don't take it up. You've got the complacents, which is I'll stay where you put me. If I'm in the opt-in, I don't opt in, recycle bin. If I'm in the opt-out, I stay there. Right? I don't actively get out. And then you've got the initiators, who when given the opportunity to opt in, they opt in. And when they're assigned to the opt-out, they don't opt out. They're just as happy where they have been put. Does that make sense? So I don't want you to go cross-eyed, but I do want to just show you this quick little egg. So basically what we've got is in some senses, got 2 randomized encouragement designs running in parallel, right? One, we've randomly sampled from the population. We assign some to a opt-in group, and some subset of those guys opt in. And then the other, we randomly sample this other group. We give them the opt-out treatment, and some fraction opt out, but a larger fraction end up taking up the program. Does that make sense? So this allows us to look at the effect of the critical peak pricing rate structure on the people who take up the program, but it also allows us to compare sort of the opt-in versus opt-out program design, right? So one of the key questions is first of all, in the first stage, back to what effect does switching the default have on program participation, right? People have looked at this in organ donation and retirement savings plans, et cetera, and have documented again and again and again, if you switch the default, you significantly increase the share of people in the program, right? There are complacents in every realm of our lives. Here, let's focus on this right here. What we're finding is that in the opt-in treatment, we had 20% taking up the program, which really pays tribute to SMUD's expert. I mean, that's high for most programs where it's an opt-in design. 96% in the critical peak pricing program if they were put in the opt-out treatment. There's some attrition in moving, but at the attrition rates are statistically indistinguishable between the opt-in and the opt-out. And to be clear, if you were put in the opt-out program, it's not like your bill came as a surprise. There were things that SMUD had to do to enroll you in the program, et cetera, but you had to really actively take yourself out of that program if you were in the opt-out program. Now, when you're thinking about organ donation, your paper stops here, right? You just want people to tick the box or not tick the box, whatever it is. So it's just, we want more people ticking the box for organ donation. If you're thinking about critical peak pricing, it's not going to help you, the utility, a whole lot if you get a bunch of deadbeats in your program who just stay where you put them and don't respond to anything, right? So if you send them a price signal and they don't get off the couch, you're really not that excited from going 20% to 96%, right? So the key here was when we nudge these people into the program, do we actually get these complacents responding and turning whatever off they're turning off and taking actions to respond to the incentives of this program? So this was one of the big questions when we suspected this might happen, but the big question is, what do those complacents do? This is what they do. I'll sort of work through this a little bit slower. So you've got your always takers and your complacents. And the red bars are the critical peak events. And the blue bars are peak times, but not during critical peak days. And so the fact that we see something here means that people are programming their thermostats. They're doing something to reduce their peak consumption, such that their peak consumption is falling even on non-peak event days. So you see, this is in percentage terms, so it's really significant, over 25% reduction among those eager beaver always takers. A lower response among the complacents, but still significant, right? Still significant. And so similarly, you see comparable but larger responses among the always takers on non-event peak days during peak times. Does that make sense? So the good news here is those guys that we nudged into the program on average, they're doing something. So the punchline here is that the average impact of the rate on peak consumption is smaller among complacents versus always takers. However, remember that we have 96% of the opt-out guys participating. So what that means is the average effect of putting someone into the opt-out treatment, the average effect of just assigning them to that opt-out cell on their peak consumption is 2.4 times as large as the average effect of putting someone in the opt-in cell, right? Because you've just got much larger participation in that opt-out treatment. Is there a question in the front row?
If you go back to the previous slide for a second. Now, the blue thing, the blue bars is savings 99% of the time. And the red bars are savings 1% of the time. So is the blue bars the big gain here?
I mean, it is a gain in the sense that you're getting, there's some fixed cost behaviors like programming your thermostat that, yeah, this is reducing. Remember, the peak days are when it really counts, when the wholesale price is really, really high. And these are days when a small...
But when it comes to, I understand that we have to control peak demand, but we're also reducing the demand year-round by 14%? Isn't that?
This is
peaks.
Oh, this is peaks. Non-critical peak days. Okay.
But it's a good question, and actually calculation I haven't done. There's still many more days where this response is manifesting. So in terms of valuing this versus this, I actually haven't done, I'm embarrassed to say. Yeah. But what this is, just a side note, what this does say is, in a non-experimental setting, one way of evaluating the impact of critical peak pricing is to use customers as their own controls and to compare consumption on critical peak event days to the same guy on at peak times during non-event days. And what this is showing you is that would give you a biased estimate of the effect of critical peak pricing on peak consumption, because the control days you're seeing a response to this rate. Does that make sense? Yes.
Do you have any data that indicates that what proportion of the complacents knew that they were in the program?
Yeah.
Like they're like you and they just toss it. Maybe they don't even realize it. So it'd be interesting to see if there was more. Obviously, you'd expect more change. At least those people who read the pamphlet and said, "Oh, I knew this."
It's a great question. We haven't done all the analysis that we wanted for this paper. What we have looked at is the survey responses, which is a very non-random sample. So the guys who are on top of things to respond to our survey, we saw no difference in the awareness of the program, but that is not necessarily a representative measure of the awareness of the larger population. What we're looking at now is heterogeneity in responses across compliers and complacents and always takers to see if there's any indication that most of this response is in a smaller subset of the complacents, and there's a number of people where it just seems like there's no action, which doesn't necessarily mean they're not aware of the program, but it's just more information we can bring to the analysis.
And was there a reason for the great asymmetry between the 9,000 and the 850? Was people afraid that there'd be too many people taking up the program, or
this year? There was some power calculations in here, and also, I think SMUD was very, it was, I wouldn't say risky. I think the world of this experiment, but there was a little bit of customers might not be so thrilled with being put in an opt-out program, so I think there was some of that going on, which will make the study big enough to get the statistical power to detect effects, but let's not go overboard here in terms of a really big sample. Okay, Carl, do we go till 1?
We go to 1.
Okay, so I think the punchline here, hopefully it's come across, is that first switching the default proves to be a really effective nudge to drive up participation, and it turns out it's a really productive nudge. You get quite a bit out of those complacents, such that on average, the response in terms of peak load is greater across people assigned to the opt-out versus opt-in. I also think this is pretty policy relevant as utilities try and think about how to most effectively mobilize demand response going forward. Okay, in the last few minutes, I just want to highlight this study. It's very new. I have no results to show you, but just another application of the randomized encouragement design, also funded by Becky and the Bloom Center, among others, and joint with several folks across campus. I think this is a nice example of engineers working happily with economists on what I hope is a pretty important project. Okay, so we've been talking about California and Michigan. If you're worried about environmental impacts of energy, we probably shouldn't be focusing on California and Michigan, or at least we should be spending some of our time focusing on developing countries, because that's where a lot of the forecast electricity demand growth is going to happen. When I got tenure, I was ready for more risky projects, and I stopped working in Michigan and started thinking a lot more about working in these developing countries where it can be a lot harder to launch these types of experiments, but it's really important to understand sort of electricity demand in these contexts. So we're looking at India, and when you think about that increase in energy demand, there's a lot of good news in that, right? Economic development, improved quality of life, et cetera, et cetera. So it's not like we necessarily want to squelch that increase in electricity consumption in these countries. What we'd ideally like to do is sort of decouple the growth in energy consumption and the growth in emissions, right? And so one way to do that, or at least one sort of lever that governments and organizations are focusing on, is energy efficiency. Can we improve the efficiency attributes of the appliances and the end uses that are driving that increase in energy consumption in these countries? And so there's some high-profile estimates of the emissions reductions that could be achieved by increasing the penetration of energy efficiency, and a lot of them assume no to low rebound. And remember rebound, we thought about rebound in Michigan, let's think about it here. I'm a newly connected household, my budget constraint is binding, you give me a more efficient light bulb, maybe I'll use more light, or maybe I'll use the savings, the money I'm not spending on the light I want to run a fan or run some other end-use appliance. That's creating, improving quality of life, but it is also increasing energy consumption relative to what we might expect if we think that all the efficient, we just multiply energy consumption by the energy savings and assume that we're sort of reducing energy consumption by that much. So just to motivate this research, there's been a lot of calls for more research on understanding the extent to which this rebound might manifest and understanding the implications of that rebound for emissions trajectories and also resource adequacy and planning. So in the interest of time, I'll just quickly describe what this is, what the experiment is doing, and then conclude. So when you think about understanding rebound, there's a real identification problem here, because when you regress energy consumption on the efficiency attributes of an appliance, you've got the classic selection problem. The people who are going to consume more energy might buy more efficient appliances, right, because it's more cost effective. So what you ideally want to do is randomly assign appliances, helicopter drop more efficient appliances on some subset of your population. And that's what we're trying to do in this experiment. So we're working closely with Graham Power, who's introducing solar microgrids and smart grid technologies into rural India. And we're randomly assigning more efficient lighting appliances across households and comparing energy consumption across these treated and control households, with the intent of asking, when you improve the efficiency of a lighting appliance, do households demand more light? Do they demand more other end uses as a consequence of spending less on lighting? This is a randomized encouragement design because we have every expectation that the households we drop more efficient lights into might trade, or they might move in the community. So we're assigning lights to increase the sort of take-up of efficient lights in a certain subset of households, but we're also going to need to track where those lights go, appliances go, in order to implement the randomized encouragement design we've been talking about. So here again, our objective here is to estimate the impact of improving the efficiency attributes of the appliances newly connected households have on their energy consumption patterns, using very high-resolution smart grid data and working closely with the engineers across campus to try and disaggregate the load data to understand, hours of light, hours of fan use, et cetera. Very new project, just getting underway. One thing I have learned is it's a lot harder to run a field experiment in India than it is Michigan or California, but we're determined. And so hopefully we'll have some results in over a year, probably. So in conclusion, I hope the main point I wanted to get across here is that I do think experimental designs have value to add in terms of informing these causal questions about the relative effectiveness and energy savings across different types of energy efficiency investments and demand response programs. There's value to add, but they're not without limitations, and some of the limitations that we didn't really get a chance to dig into, but I wanted to flag, because these are not silver bullets here. External validity concerns, what we learn in Michigan, is not necessarily true in Ohio and California or Vietnam. And spillovers, to the extent that there are spillovers between people, peer effects, all sorts of interactions between treated and control households can introduce bias and complicate the interpretation of the results. So with that, I'll conclude, and thank you for being here.